Welcome back. In our previous session, we laid the groundwork for understanding the fundamental challenges in distributed systems. Today, we're diving hands-on into a critical component, building a robust, production-grade distributed log collector service. This isn't just about collecting files, it's about creating the foundation for observable systems that process billions of log entries daily, much like Netflix or Uber. By the end of this lesson, you will be able to understand the core architecture of such a service, implement resilient file system watching strategies to detect changes in real time, and apply advanced patterns for exactly once processing and back pressure handling. We'll also integrate crucial elements like circuit breakers and distributed tracing to ensure your collector is both robust and easily debuggable in a production environment. Let's get started on building a system that truly scales. The first critical step in any log collection pipeline is knowing when and where new log data appears. Traditional methods of periodic file scanning are inefficient and introduce unacceptable latency. Our solution leverages Java NIO2 watch service, which provides real-time event-driven detection of log file changes. This means we're instantly notified when a new log entry is written. However, relying solely on events can be risky. High I/O scenarios might cause events to be lost. To counter this, we implement a hybrid approach, combining immediate event-driven watching with periodic validation scans. This intelligent fallback ensures we catch any missed events or handle complex scenarios like file rotations. Finally, our reconciliation pattern periodically compares our in-memory state with the actual file system, guaranteeing that no log entries are permanently lost even during system failures. This dual strategy ensures both speed and reliability. Once logs are detected, ensuring they are processed exactly once is paramount. Distributed systems face the challenge of duplicate events or lost data due to restarts or network issues. Our log collector tackles this with distributed offset management. We use Redis as a coordination layer to store and track the last processed position for each log file. This way, if our service restarts, it knows exactly where to resume, preventing both duplicates and data loss. This pattern carefully balances consistency with availability, prioritizing performance while ensuring recovery from any failure point. Beyond integrity, we must also handle unpredictable log volume spikes. A single service can generate gigabytes of logs in minutes. Our system implements adaptive back pressure using Kafka's built-in flow control, combined with local buffering. This prevents our collector from being overwhelmed, dynamically adjusting buffer sizes based on downstream processing rates, maintaining low latency during normal operations, and gracefully handling bursts. A production-grade log collector must be resilient to failures in downstream systems like Kafka or Redis. Naive retry logic can actually amplify problems, leading to cascading failures. We prevent this by implementing the circuit breaker pattern using libraries like Resilient4j. This pattern allows our collector to fail fast when a downstream service is unhealthy, preventing resource exhaustion and giving the downstream service time to recover rather than continuously hammering it with requests. Crucially, these circuit breakers aren't static. They use adaptive thresholds that adjust based on historical success rates, avoiding false positives during normal load variations. Finally, to debug issues in a distributed system, you need visibility. We integrate distributed tracing using tools like Micrometer and Zipkin. This creates an end-to-end trace for each log entry from its detection to Kafka delivery, making it incredibly easy to observe and diagnose collection issues in production. This ensures your collector is not just robust, but also observable. We've covered a lot today, building the critical first component of any distributed logging system. Let's quickly review our key takeaways. We learned that a robust log collector is absolutely vital for creating observable systems, serving as the foundation for monitoring and debugging. We explored essential patterns, including the Java NIO2 watch service for real-time file monitoring, distributed offset management with Redis to ensure exactly once processing, and adaptive back pressure to gracefully handle unpredictable log bursts. Furthermore, we integrated powerful resilience and observability features by implementing the circuit breaker pattern to prevent cascading failures and distributed tracing to provide end-to-end visibility into our log events. These patterns collectively ensure your collector is not just performant, but also incredibly reliable and scalable, translating directly to hyperscale production environments like Amazon or Google. Now, for a quick self-assessment,
how do these patterns prevent data loss or system overload in a real-world scenario? Tomorrow, we'll build on this foundation by implementing intelligent log parsing. We'll add pattern recognition, structured data extraction, and schema validation, transforming raw log streams into queryable, analytics-ready data structures that feed business intelligence systems. Get ready to turn noise into insight.